So I'm going to start, and I'm also recording it. So I'm not going to do much. Well, we will do many things today, but most of it will be heuristics because I don't want to do serious calculations in an online class. First of all, I want to discuss some issue which we had kind of skipped, and it's kind of important. It's about because the paths we have been discussing so far were all mostly time-like paths. So we had these word lines, and we said, well, this doesn't look like a time-like. And we said that the tangent vectors at each point has this property that its magnitude or scalar product with itself is normalized to -1. In any case, you cannot change its sign. You can change, if you change the flow of the parameter, you change this 1 over here, but you will get some constant which is negative. But this was fine for us because we said nothing moves faster than speed of light. Although one of your homework explores the idea that if we allow that some white lines, some particles do have white lines which are not time-like, which do have something like this, a positive number, what happens then? But even if I ignore those kind of faster than light particles, I have to definitely consider light itself. So light's path does not obey this. So what is the path of light? Path of light, or in other words, the word line of light. How to describe it? We can start in the idea is that I want to describe it geometrically, that what is the geometry of this one line. But to get to there, I can start in the special inertial coordinates because I know how the things work in inertial coordinates. Write everything in such a term that I can then generalize it into any arbitrary coordinate system. So um, for in inertial coordinates, I know that the light's path coordinates, light's path is, or light's word line has to be, if I'm just considering one spatial dimension, but you can easily generalize all this discussion to any number of spatial dimensions. We know that it has to be of this type. X naught is equal to plus or minus 1 x1, right? Because in inertial coordinates, the light is at 45 degrees. Now I want to write it as a parameterized equation. So how can I do that? Well, it's easy enough. If I choose something like this, x naught lambda x1 is equal to lambda, this will give me this follows this with a plus sign, or I can choose this one. This will give me this branch of the light's word line. So I can do I can take these, and these describe for me the parameterized equations for the world line of light in inertial coordinates, it must take one of this path. Well, you can object that I can even take this thing, lambda square or lambda cube or any other function of this parameter, as long as I give the same function to x0 and x1, these equations will still be satisfied. So can I do that? We will explore it in a little while, if that is allowed or not. But let's first stick to this one. What does it give us? So it tells me that if I take this, that the tangent vector of light is, its components are 1, 1 or 1, minus 1. That means the normalization or the scalar product of it is minus g mu nu t mu t nu is simply minus 1 from the matrix, then matrix is diagonal, so I get this guy twice, plus 1 from the matrix and this guy twice, so it's 0. And it doesn't matter if I choose this one, because then I again get minus 1 square, which is again 0. So light follows the world line whose tangent vectors are have norm 0. Well, actually, even if I had chosen any function of lambda, this conclusion would still be true. Still gives t mu is equal to 0. So far, I can keep any general f of lambda. I can parameterize it with any function of lambda. And as long as I keep the same for x0 and x1, except for a plus or minus sign, I will still have I will still make this conclusion that the light's world line is the one whose tangent vector has a norm 0. So this kind of curve, this is called a null curve, whose tangent vectors have norm 0. Now, and so they have norm 0. Now that means I can, if I do it this way or do it with some faster parameter lambda, or any omega times lambda, I still get t mu is 0. This is unlike what I had for the material particles. For material particles, I knew that u mu, by hand, I had to normalize it with minus 1 as minus 1. And this happened for very special uh, parameter. What was the parameter? The parameter had to be proper time. One very specific thing, because it was actually in other words, it was parameterized with the length of the curve, with length defined with an uh, extra minus sign over here. Well, we can write it as a differential. So we were parameterizing it with the length. So very special parameter, proper time. For these curves, the length, the metric is giving us 0. So there's no length over here. So I cannot parameterize it with the proper time. There's no proper time over here. No clocks moves between these 2 points along this path. And if I don't interpret it using clocks, I just measure its length using the metric, then I get a 0. So I don't have a uh, preferred parameter. So remember, if I have one parameter lambda, then all others lambdas which are linearly related to them affinely related. They also they also satisfy the um, geodesic equation in the simple form without the extra terms. But out of these different available affine parameters, in case of material particles, we chose even from here something special, the one which was equal to the proper time. Because when you change this parameterization, obviously the components change. These components, they scale, and what you create out of these, it changes. And for a very particular parameter, you get -1. While over here, that's not happening. On this side, you have 0. So if you scale them with the same factors, it doesn't matter. You still get a 0 on the right-hand side. So the scaling doesn't matter. So how to choose, or do we even bother to choose one of the special uh, parameter out of this? Well, there is this idea that in case of material particles, by material I mean things which move at less than speed of light. We had defined the momentum for vector, which was just the scaling of the tangent vector. This is the properly normalized tangent vector. There was some scaling related to every particle. And when we scale in this way, this tangent vector, we call this the momentum for vector, whose first component was the energy, and the second component was the momentum. So we can retain the same idea that we say that now we do not scale it with anything, because scaling is kind of redundant, because we can scale in 2 ways. Scale it by putting something over here, instead of m, or scaling it just by changing this parameter. So again, for light, I define p mu as dx mu over d tau without any rest mass coming over here, without any scaling parameter coming in front. But this is not well defined because, well, I shouldn't write it as tau because there's no proper time, some L, because I can choose many different lambdas. They're all at equal footing. So I say that I choose, now here I use Einstein's idea, or maybe, well, it was presented by Einstein, but it's like part and parcel of quantum mechanics. I know that that the energy of that light acts as particles, which are photons, each of which has energy equal to h bar. This is just some constant called Planck's constant times the frequency of light. So if I again put this, use the units where h bar is 1, energy is just equal to frequency. Now I say that I have different kinds of lights of different frequencies, or in other words, different energies. Actually, I don't even have to use this quantum mechanical idea. I can say the same thing in a different way as well. But I'm going to say it in both ways. So I say, using this equation only gives me some idea how to interpret it. So I know that P0, if I want to, in case of material particles, I call P0 as energy. So if it's still energy, then this better be equal to omega, the frequency of the light. But this frequency is something measurable. I know that if it's red light or blue light or green light, whatever its frequency is. So I say that for each kind of light, I choose the lambda in such a way that this tangent vector, the zeroth component of it, matches with whatever the frequency of that light is. So that's how I fix my this affine this parameter lambda. I choose that lambda which has proper scaling so that I get dx naught over d lambda equal to omega, which is frequency and also which is energy by this formula. So if this is the energy, then what is the momentum? It's also is dx1 over d lambda, but I know that it's equal to, is same because it's a null vector. So the zeroth component and the first component are same, plus or minus. All that you have is a plus or minus. So that means that this vector for light will take this form. This is momentum for vector, which is just the tangent vector properly normalized. You want to say normalized, or you can also say, or you can think of it as properly parameterized, or you can say that the curve is properly parameterized. Properly parameterized to give you for tangent vector components to match with frequency of light. So it's actually a good thing that we have this freedom in case of the null vectors, null curves, that uh, there's no special parameter, distinguished parameter available. We can choose many different, because now we can use this freedom to interpret the frequency of that light. I just match the parameterization in such a way that the zeroth component of the tangent vector gives me the frequency of the light. So is this clear? Any question? Okay, if this is fine. Now, if I now use this, that I know that this is a null vector. So this implies minus p0 square plus p1 square is equal to 0, or p0 square is equal to p1 square. So this is just E square is equal to p square plus m square, our equation which we had got for material particles, except I have to put m is equal to 0. So that's why people say that photons, and this, remember, this was the rest mass. Photons have rest mass 0. Well, you don't have to define any rest mass for photons, but if you want to stick with the same equation, well, yeah, you have this part of equation, so you may as well add an m square and say that the m is 0, so that this equation applies to everything, and it applies to photons with m is equal to 0. The other equation, this one, remember over here, it wasn't the rest mass. It was the relativistic mass, m naught over 1 minus v square, c square, v square over c square. So this is fine, except that it's not useful now, because m naught is 0 and the denominator is also 0. So it's indeterminate. E could be anything. And so the only useful equation is this one. Now, so one issue is that out of all these affinely related parameters, I pick one which is appropriate for the whatever frequency I'm using. This is not important at all. This is just where you're starting the 0 of your parameter. The only thing important is the scaling. But what if I use this square weight or something like that? I saw that it still gives me a null vector, but would that be fine? Well, if I parameterize my equations like this. So first of all, let me write a parameterization which is according to this. This I can write like this. This will obviously give me dx naught over d lambda is equal to omega, and dx naught over dx1 over d lambda is equal to omega. So it will give me this momentum vector as omega, which I want. So just parameterize in this way, and on this constant omega, just put it equal to the frequency of the light. But what if I parameterize it with something like this? Lambda square, maybe I can put a constant here. This still gives me a null vector, null tangent vector, but it has some other problem. So if I do dx naught over d lambda, I get 2a lambda. I do another one, I get 2a. But I'm working in Cartesian coordinates. No, sorry, in inertial coordinates. And in inertial coordinates, I am in inertial coordinates. Where the Christoffels are all 0. So that means my wait. That means my geodesic equation should take this form for each one of them. Because on the right hand side I have nothing. The Christoffels are 0. But this equation, I see that if I choose this parameterization, then my coordinates, my path doesn't follow the geodesic equation, which I know is not a problem because geodesic equation is followed only for some special parameterization. For if I do, which we call the affine parameters. So if it holds for a particular parameter and I make a nonlinear transformation on it, then the geodesic equation does not hold. Well, we will see later that the term which appears is kind of is actually expected, but the simple form of the geodesic equation which we have been using does not hold. So that means I shouldn't be using this. And what the correct way to think of it is that you have a geodesic equation and you solve it. It tells you what kind of parameter you should be using. So the parameter you get by solving the geodesic equation is the affine parameter. But the geodesic equation will only tell it to you up to a scaling. And out of these, then you select further based on frequency. So that means the correct equation, correct path, or correct word line, which describes the path of the light, you give it using parameters, has to be for light, has to be null, but also you have to make sure that follows the geodesic equation. So these two conditions fix what path or what word line the light follows. So this is called path of light or word line of light, which satisfies these two conditions, is given the name the null geodesics. And word line for material particles, they are time-lag geodesics. And if you had things moving faster than light, there would be space-like geodesics, and people give them name tachyons, but they probably don't exist. But obviously these two are extremely important. Now, we have done all of this in using our intuition and using the easy mathematics of Cartesian or inertial coordinates. But these conditions which define the path of light, now they are not dependent on any coordinates. You write the path in Cartesian, which satisfies these two. But the first condition is all it's saying is the following, that the path has tangent vectors such that the norm is 0. That's the null condition. Now this is a contraction. It's a contraction, so holds in any coordinate system. And remember, this is what I'm taking to be as a geometric definition, holds in any coordinate system. So this is geometric. All it's saying is that the tangent vectors have norm 0. And this is a completely coordinate independent statement. The norms of tangent vectors, they are constructed through the contractions with the metric. They're not dependent on any coordinate system. Once you contract all the indices, whatever you get is a scalar. That does not depend on the coordinate system. Similarly, the other condition, we had it like this. But we know that this side is not coordinate independent. If you make an arbitrary coordinate transformation, takes it to, changes this equation to the geodesic equation. This was just a special form. This is just a special form in the Cartesian coordinates. But I can just write this. This holds in any coordinate systems. It's coordinate independent. So in other words, this statement that's a geodesic, that statement is coordinate independent. That holds, if you write its equation in different coordinate system, the partial differential equations you get are different in different coordinate system, but the path is defined without any reference to those coordinate system. It's a geometric meaning. It's just the path of the extremal length between those 2 points. So if I take these 2 points and I look for a path of extremal length, which is also null, then that would be a null geodesic. And it has nothing to do with any coordinate system. Now, so this was just something which we had skipped discussing before. Any question before we move on? Okay, so
No, sir.
now what we are going to move towards is studying manifolds or curves. You can call surfaces, but the better to call them curved spaces. But I won't do that today because I don't really want to do it online. But what I want to discuss today is that why do we even need them? What is the idea behind that why do we need to study curved spaces in order to study physics, which we are doing. So I'm going to discuss some heuristic arguments because when you're developing a theory of physics, you are just guided by some experiments, some ideas. You don't like it's not God given, it's not just existing over there. You have some ideas and you want to try based on those ideas that what will work. So based on your intuition, based on heuristics, you develop a well-defined mathematical theory, and then you compare with experiments. That does this theory which I have written down, does it correspond with experiments or not? If it does, it's fine. If it does to a certain extent, you accept it as a good theory, but it will never fully um, um, correspond to experiments. Later in time, you may encounter some experiments which it does not fully explain. So then you fine tune it, you refine it, or you try to find a better theory. So Einstein had some ideas that how the gravity should work, and he was guided by some intuition. And when he applied that intuition, intuition, I think, to a layman would have, well, not even layman, to many physicists would have probably appeared kind of crazy way to go about it. But I think he was very smart to realize that this is the right way to go about it. And when he wrote the mathematical theory, that turned out to be actually corresponding to our universe. It explains so much of about the universe that we haven't found any contradiction to it with the uh, with any experiment so far. And actually, the form the theory takes, even the form is so beautiful, and it's written in such terms that you realize even if there were no experiments to test it, and all it gave you was reproduce Newton's theory. So it was, in a sense, an explanation of Newton's theory. The moment you look at it, you realize that you have discovered something deeper. It's a deeper explanation of gravity than Newton's theory, and it does it in a geometric way. So where does this, what are the ideas behind it? So that's all I'm going to discuss today. So the first thing is the equivalence principle. So they say, I don't know, I mean, if it's really happened. So they say that there was some guy who fell from a tall building and he survived. So Einstein went to him and asked him, how did you feel? He said that I felt that I had no weight. But then again, I don't know if it happened or not. But Einstein did imagine this thought experiment. He was very good with these thought experiments. And when he did this experiment in his mind, he says that it was the happiest thought of his life. So, what's the equivalence principle? In a sense, this principle originated again with Galileo. So, what was the principle? If you have the leaning tower of Pisa, you throw different objects, they all fall at exactly same rate. Gravity affects everything in a way to give them same acceleration. So as if the mass doesn't even matter. And so this observation that meant something for Einstein. So what did he say? Well, he said if you are in an elevator and you have different these objects, a hammer, a leaf, a big ball, an apple, whatever, and the cable breaks. So it's a freely falling elevator. So what will you observe in this elevator? You have a meter stick over here, and you probably have a clock. Since everything falls at the same rate towards the earth, that means on this meter stick and on this clock, there is no gravity. Everything just floats. So you find no forces, no force of gravity on anything on this meter stick and clock setup. So Einstein said, this looks like a better reference system to use than the one where you are standing over here on Earth and you have a meter stick here and all these things are accelerating. Why? Because on this reference system, you have to invent forces. You have to complicate your physics. So he said, well, maybe this is more like an inertial frame and not this. And he gave a very nice argument for it. I don't know how did he presented it, but let me present it to you. It looks like a crazy idea that you say that this is not the natural frame, this is not the inertial frame, this one is the inertial frame, which is falling freely. And this is the natural frame to do your physics. But that's what you should be doing actually. Because suppose you have a bus and there's a meter stick over here. And someone is standing over here. They have a meter stick. And over here, you are standing and there are objects. There's a hammer, a ball, a leaf, an apple, and some big mass. So when the bus starts from zero and has some acceleration, so what's going to happen? You're going to feel like someone pushed on you. Why do you feel like? Because the bus moves forward and you stay there, but on the meter stick which is stuck to the bus, you say what happens is first you had zero velocity and suddenly you started gaining some velocity according to this meter stick. Well, first of all, you would say maybe there's some imaginary force. I literally felt like someone pushed on me. So maybe there is some imaginary force which is acting on me. And you had heard about magnetism, so you think like maybe there's some magnet inside the bus and it has in me. Maybe there are some angels pushing on me. I don't know what, but there was a force because I did not maintain my speed, which was zero, on this meter stick. I started accelerating. So there's some force. And there's some force on this, there's some force on this, there's some force on this, all of these. But you realize that there's some curious fact about this force. That this hammer, which was heavy, there was a larger force on it. This leaf, which was lighter, there was a smaller force on it. And this big box, which was much, much heavier, there was even a larger force on it. So there was this conspiracy of these forces was going on, and the forces were being adjusted so that bigger masses have bigger forces, smaller masses had smaller forces, so that in the end, everything had the same acceleration. And you say, well, there's some kind of a hidden force inside this bus, but it's a very conspiratorial kind of force. Then you ask this guy standing here. He tells you, actually, on my meter stick, none of the objects moved. They all stayed there. They were stationary and they remained stationary. And it was only your meter stick which was accelerating. So your reference system, defined by your meter stick, was an accelerated reference system. It wasn't a good one. Mine is good one. Why mine is good? Because the Newton's first law holds in mine. Holds in on the meter stick on ground.
Sir, question.
एक second है. So that was the definition of inertial reference frame. The reference frames where Newton's first law holds. Physics is simple. So he says there's no conspiracy going on. All of them were just stationary. It's only that your bus, the meter stick on your bus was accelerating. So no wonder the markings started slipping and everything appeared to be accelerated on your meter stick with same acceleration. So no conspiracy. And you will immediately realize, yeah, maybe you have to be right. If everything is moving, is having a same acceleration, then it probably is my meter stick which is accelerating, and not there are not any forces. And your meter stick seems like a good one, is an inertial one, because things maintain the speed on your meter stick. Yes, what's the question?
सर आई जस्ट वांटेड टू कंफर्म मीटर स्टिक जो है वो मूव नहीं कर रही है ना, सिर्फ बस मूव कर रही है.
नहीं, मीटर स्टिक
Meter
भी बस
stick-
के साथ मूव करिए. मीटर स्टिक इज अटैच्ड टू द बस.
अच्छा. ओह राइट सर. ओके.
So now there was Newton sitting under a tree, and an apple fell on his head. Newton said apple did not maintain its initial speed, which was 0. It started gaining an acceleration. So there had to be a force. And he said there's force of gravity. There was Einstein over here. He said, well, wouldn't it be better to think that the apple stayed there and you accelerated to meet, your head accelerated towards the apple. So apple doesn't fall. It's actually you who are falling towards the apple. Newton replies, well, obviously you can talk in this fancy way, but it's useless. Why you want to complicate things? Einstein tells him, well, I'm not complicating things. It's you who are complicating things. Because if I go back to this lift, compare it with this bus. What's happening in the meter stick of Newton? This is Newton's meter stick. This is Newton. What's happening on Newton's meter stick? Everything is accelerating, but everything is accelerating at the same rate. So he had to invent this conspiracy that the force of gravity, it keeps adjusting. You get exactly the same amount of force as much as you have the mass. Einstein says, well, I have a better meter stick, just like this guy on the ground. And on this meter stick, nothing is accelerating. It's your meter stick which is accelerating. So it's actually you who are going up to meet these objects. And these objects, as on my meter stick, they are stationary. So the force of gravity is just like the force in the bus. Force of gravity is fictitious. What do I mean by fictitious? It's just there because of using are wrong. Well, there are no wrong in only in the courts. There are no wrong coordinate system. You can use any coordinate system you like. But of using a wrong coordinate system, by wrong we mean accelerated. And the acceleration in this coordinate system which you feel is because if the fact that you observe particles accelerating in this coordinate system is only because the meter stick itself is accelerating. And he says that there are better meter sticks around. They are better. By better I mean inertial. Why better? Because physics is simple. No other way, no other reason. Otherwise, you can use any of the coordinate system. They're all just labeling. But in this, physics is simple. There are better coordinate systems around where there is no force of gravity. Because force of gravity was just an effect of acceleration. So if I go to an inertial coordinate system, I don't have these objects accelerating, and they're just following Newton's first law. So falling lifts are the inertial coordinate systems. So that's his idea. You can believe it, you don't have to believe it. It's his starting point. And based on this, he will develop his theory, and then we compare that is it giving us the real world or not. Inertial frames are the freely falling frames. And there's no force of gravity. Any question so far?
No, sir.
बाकी लोग?
No, sir. No, sir.
Okay. So but then Newton comes back and he says, you're just trying to be over smart. If this is really true, and okay, let's do one more thing. So if I use the freely falling system, falling coordinate system, and I draw the space-time diagram of objects using that system. So your lift is falling. There's a meter stick and there's a clock. And these objects are present here. I follow the motion and draw their whirl lines in using this meter stick and clock. What will I get? Obviously, I'll get straight lines. That was the whole point. That the motion of these objects is very simple. It's just described by straight whirl lines. In the system which is on the ground, it won't be straight lines, it would be curved. But you know that if you use a wrong coordinate system, straight lines, if you just plot those as your coordinates, straight lines will not look straight lines in those coordinate system. Their geodesic equations, the straight line equations in those coordinates are different. So no wonder if you plot using those coordinates, you get other kinds of lines. So that's the kind of relation between this. Geometrically speaking, they are following straight lines, but they appear curved in wrong kind of coordinate system. So for example, if I use r and theta, and so this is x and y, which are the nice coordinates for plane. Nice again in quotes, because any coordinates are fine. They're nice because things are very easy to interpret in them. So for example, you can very easily tell the straight lines. The geodesic equation is just that so in other words, the acceleration with respect to the parameter is 0, which translate over here as that the acceleration of these objects is 0. But if this same straight line I draw in r theta, so on here I draw r and over here I draw theta, lines of constant r, lines of constant theta, and make this mesh. This same line on this mesh will look complicated. Will look like this, something like this. But I know it's a straight line because I can check its geodesic equation. So that's the kind of relation which is going on in simple physics and complex physics. It's just that you are using complicated coordinates to describe it. And the fact that in the falling lift you get the straight lines which appear straight to you when you draw the coordinates, which they actually appear straight to you when you draw the coordinates, because those coordinates are the nice ones. So this is the nice coordinate system, and since they appear straight to you in this coordinate system, you say that this is a proof that there is some coordinate system where these particles lines appear straight, so they are straight lines, and these particles have no forces on them. But then Newton is embarrassed. He thinks about it and he tells Einstein, well, you try to be smart, but the nature does not work according to your wishes. Because he says, in all of this analysis, you had to assume that the value of g is constant. Acceleration due to gravity is constant. And its direction is also same. And this is probably would be true if you are just working in a small lift. In a small lift, it's true. But it's not true over large distances. So if the gravity is directed towards the center of Earth, and if these two lifts are following, what is his coordinate system? Is this mesh of meter sticks which are freely falling, while there's another lift over here. Its mesh is this. When this guy, he drops an apple and he plots the lines, the one line of this apple according to his mesh, he gets a straight line. Maybe if the apple was just dropped, it will be a vertical line. While this guy, when he drops an apple and draws the space-time diagram of his apple, he also gets a vertical line. But these vertical lines, they do not match with these. And actually they are coming, these two apples are coming closer as they fall towards Earth. So what will happen is that if I extend the space-time diagram of one of this lift, his apple will have a line like this, but the other apple will be coming closer to him. The two lines will be bending towards each other. Maybe if I can consider a third lift here, some compromise, I will see that the two lines are coming towards each other. But if I ask individual one of them, what about the apple in your coordinate system? Your apple in your coordinate system, they say it's a straight line. The other guy says, my apple in my coordinate system is a straight line. But when I consider both of them, then the apples are coming closer to each other. And actually, the acceleration is not in the direction where you expect it, in this direction. It's like pulling them towards each other instead of pulling them down towards the center of Earth. So Newton says, okay, maybe my idea was wrong. There is no force towards the center of the Earth, but what about this mysterious force which is pushing these things together? Well, you can consider a satellite. It's going around Earth. You drop this is also an inertial system because it's freely falling. You drop an apple. In its frame, the apple is a straight line, doesn't move. But obviously it's rotating around. So according to this lift, it has acceleration. So that means that these inertial systems which we have discovered, they do not extend to large distances. Not large distances and not large times, because very soon this lift is gonna fall to the center of Earth and probably get destroyed. So they do not extend over large periods, large distances. They're inertial only in a small region. What region? Where you can take G to be constant. Even if this lift were very long, then the apple at the top and apple at the bottom will not have same G. And if they do not have same G, they will feel a relative force with respect to each other. So the lines which you draw, the mesh you draw on the top will not match with the mesh you draw downstairs. So Newton said, what about this? Einstein thought about it, and Einstein realized that this could be this phenomena. And it's not a very strange phenomena. We have known about it all along. He said maybe all you have is this. So if I consider the surface of a sphere and I locally demand that I'm going up and I'm just going to follow a straight line. So you keep going up, you're just going in a straight line, the straightest possible line. And this guy, so you ask this, there's an ant over here going up. You tell them, just go straight up. And this ant, this also goes straight up. They didn't cheat. They were both going straight up. They both said we are following straight lines. So like those apples, their world lines were following straight lines locally in their region. But still these straight lines start coming together. In other words, the inertial system, this is a hallmark of a curved surface, that if I draw a Cartesian coordinate here, because of the bending of the surface, this doesn't remain Cartesian on the other side. Or even if I forget about any coordinates, this happens. We know that this phenomena happens on curved surfaces, that a line which is straight two lines which are straight, and if they are parallel in the beginning, this can still come together. So he said that maybe what is going on over here, this situation, that they both claim that we are straight lines, but they're coming together. So that's exactly what's happening. These are the straight lines, and they're not coming together because there was a force and the straight lines turned into curved lines because of those force. It's just that the underlying geometry is curved, and these are the straight lines which are because of the geometry coming together. So he said, I can save this my idea, which is the equivalence principle, which you can state as gravity is indistinguishable from acceleration, or this is also equivalent to saying that the freely falling frames are inertial frames. This idea can be saved if I assume that locally these are inertial frames, but globally the geometry is curved, and that gives some extra effects. And if I have to describe the gravity, I will have to take care of the curvature of the space-time as well. So this was the whole idea. And he said, for example, you can describe, well, like if you have a line, if this is the one line of Earth, and this is the one line of Moon. Moon is rotating around Earth, so something like that. He said this spiraling path, which looks spiral to us in this some kind of global coordinates which we are drawing, is actually not spiral. It's well, it looks spiral, but it's a geodesic. It's a straight line in this wrapped geometry, which has been caused by the presence of Earth over here. So his idea was that there's no force of gravity. Things just follow. Their one lines are just geodesics. They're just straight line, just as in case of without any planets around. But what happens when you have a planet that they still follow straight lines, everything just follows straight lines. They don't feel any gravity. But it's just that the presence of planet causes some curvature in the space-time around. And then his goal was how to describe this curvature. Well, describing the curvature is simple because the mathematics was fortunately invented just some time ago by Riemann. It wasn't known to many people, but Einstein realized that he has to describe it using curvature. So he went about and learned about Riemann's way of describing curvature. But then the next task was, how is it curved? How do you describe how the planet is going to curve it? In what fashion? Curvature being there is just a kinematic statement that there is curvature. But what kind of curvature? What governs it? So for that, he had to come up with some equations, which are the Einstein's equations. So now our goal next would be to learn how to describe curvature and then derive that what equations should govern that curvature. Now, should I go on to go to some heuristic of curve geometry? I think maybe we can stop here because I don't really like to teach, especially a course like general relativity online. It just seems like I'm talking to myself. Okay, let's stop here and we will discuss next time how to describe curvature in general, and then how to do it for space-time, and what are its effects on physics, and finally how to set up some equations which will describe which will describe how the planets or how massive bodies affect the curvature of space-time. So any question?
सर वो पिछली रिकॉर्डिंग और इस वाली की रिकॉर्डिंग अगर प्रोवाइड हो जाता
वो रिकॉर्डिंग मैंने कोशिश तो कर रहा हूँ, यूट्यूब अपलोड ही कुछ नहीं होने दे रहा। आई डोंट नो उनके सर्वर बैठे हुए हैं या उनके क्या स्टोरेज का मसला है, क्या मसला है उनका। तो वो जैसे ही वो होता
सर
है वो
आप
मैं
अपनी ड्राइव पे बस कोई भी लिंक ड्राइव लिंक बना लें और उस पे लिंक शेयर कर दें आप अपनी ड्राइव पे ही रख के, तो
चलो
उसमें
मैं
लोड
देखता
करने की
हूँ।
भी जरूरत नहीं पड़ेगी।
आई डोंट नो, आई मीन वो काफी
Thank you, sir.
बड़ी फाइल होगी, तो कहाँ से शेयर हो सकती है?
सर ज़्यादा एमबीज की नहीं होगी वो,
अच्छा चलो मैं देखता हूँ।
वन ड्राइव पे सर आप अपलोड कर दें।
चलो वन ड्राइव पे कर देता हूँ।
सर नेक्स्ट
Thank you,
नेक्स्ट
sir.
क्लास हाइब्रिड हो सकती है?
नहीं,
ऑनलाइन
हाइब्रिड में नहीं
और
करना चाहता कोई क्लास।
ओके सर।
ओके